How can we graph the function y being equal to e to the power of minus x squared? And if we integrate this guy from negative infinity to plus infinity, how much would it be? Okay. This guy is very important because it very looks like our normal distribution function. How come? Well, if you remember the functional form of a normal distribution, it looked like y being equal to 1 over 2 pi e to the power of x minus mu sigma, the whole thing squared. Holy cow, it looks awful, you may say, but if you think differently, this guy, you can think of it as whole x, okay? And then this guy, well, is, you have some scalar multiplication, and the remaining part, this guy, e, the same, and minus power, and then some squaring of it, okay? And we have some scaling factor 1/2. So that's some manipulation you're going to do it later on, but it's deeply related to each other. You see the square term, okay? So it's going to be a bell curve. It's going to be a bell curve, basic bell curve. And then the evaluation, okay, if you do this integration, it's going to be square root of pi. Okay, square root of pi, which means it's going to involve circle when you integrate this thing. Okay, and then you have to square it somehow and then get it back. So that's why you have a square root of it. And this guy looks awfully like this one over here, but this one is in the denominator, okay? Whereas this guy is just the numerator part over 1, okay? So there must have been some scaling going on as we move from here to there, okay? That's the big picture. So how does that work? Well, this video, I'm going to go through this e to the power of minus x squared first, and then try to evaluate this guy, okay? How can we draw this graph? Well, e to the power of x, well, draw x-axis and y-axis, and 0, y being equal to e to the power of negative x squared, okay? And then when x is equal to 0, it's going to be what? 1, because that's e to the power of 0 squared, which is 0 minus. So 1, it's going to go through. And if x is equal to either plus 1 or minus 1, it's going to be e to the power of minus 1, okay? E to the power of minus 1 when x is equal to 1 or minus 1, okay? So e to the power of minus 1 means 1 over e close to 1/3 or something, okay? So roughly speaking, it's going to be passing 1/3 point over here, okay? And then as x goes to infinity, it's going to converge to 0, but always positive. And goes to negative infinity, the same thing, always positive, but asymptotically converging to 0. So those parts, we can see that, and it's going to be converging like this, okay? I have to make sure it's not touching it, okay? Two things like this, and it's going to be converging like this, very fast. Now, what about this area, okay? Is it going to be pointed like that or round, okay? It's going to be rounded over here like this. Very smooth, rounded, okay? Exactly a bell curve, exactly a bell curve, okay? How come? Right? Because we know in the previous video we learned that y being equal to e to the power of x will go through this like this, okay? But both graphs pass through these 2 points, and as x approaches to 0, well, this blue curve, it was approaching 1, and then the black curve has to approach to 1 as well. But the speed of approaching 1 has to be different, because this guy versus e to the power of minus x squared, right? This is a square term, whereas this is a linear one, okay? The comparison between these two is exactly like the comparison between the line and parabola, okay, line and parabola. So if I draw line and parabola, okay, here is y being equal to x line, and then the parabola will look like what? Will look like, let me go through this part. The parabola y is 1, 1, and then minus 1. Over here, the parabola will look like this. Okay? So over this interval, well, purple parabola is closer to 1, okay? Closer than the green line, okay? So the same idea. Over this interval, right? Okay, between 0 and minus 1, over this interval, the blue graph will be approaching 1, but the black graph will be approaching 1 faster because of this kind of relation goes on for the bell curve, the black line, okay? And very smoothly, and then moving through, okay? So in the end, it's going to be our usual bell-shaped curve, okay? Now the question becomes, how can we integrate this guy, okay? Integrating this function is waiting for you in the next video, so wait for that. Thank you.